Welcome. So, we are looking at the solution for the diffusion equation, which is this, and the Corn-Hilliard equation, which is this, okay, some d tilde. This d tilde is not the same as this times some g function, which is nothing but dou f 0 by dou c function minus 2 kappa. So, there is a del squared acting on this and del power 4 c acting on this. So, that is the equation we are trying to solve. If we do Fourier transform, then we can solve these equations. Fourier transform technique is much more accurate than finite difference, and in that case we take the Fourier transform t plus delta t minus c tilde of t by delta t is equal to d tilde, and Fourier transform basically gets you minus k squared, in this case c tilde. So, and at time t. Okay. So, you can then write c tilde t plus delta t as nothing but c tilde t by 1 plus d tilde k square delta t. So, this can be at t plus delta t. So, this can go, and that is how you evolve the solution. So, this is implicit technique. So, everything on the right hand side is at time t plus delta t. So, you can evolve very fast, but in this case such a trick does not work. That is because if you do the Fourier transform, c tilde t plus delta t minus c tilde t by delta t is equal to d tilde. Now, this del squared acting on g. So, I have to take minus k squared g tilde, but this can only be at time t. It cannot be at time t plus delta t, because at t plus time delta t I do not know c, and the g function is nothing but 2 a c into 1 minus c into 1 minus 2 c. Okay. So, that is the reason why this has to be calculated in a real space every time, and that quantity should be Fourier transformed. So, that can only be at time t. On the other hand, the other term minus 2 kappa k power 4 c tilde, this can be at time t plus delta t. So, if we now look at it, so it becomes c tilde t plus delta t is equal to c tilde t and then this minus d tilde k square delta t g tilde time t divided by. So, this is goes there. So, it comes 1 plus 2 kappa k power 4 delta t is the solution. So, this is known as semi implicit spectral technique, because some parts is implicit, some part is explicit. So, this is why we call it semi implicit, but semi implicit is still better than explicit, because it will still allow you to take larger time steps. So, now I have two scripts which implement this, and remember, because this is Fourier transform, the periodic boundary condition has to be incorporated, and that has to be incorporated in terms of this k lying in the range of minus pi by a to plus pi by a. So, that is how the periodic boundary condition will be implemented in this code. So, what we now want to do is to write the Fourier spectral technique code for doing diffusion equation first, and then the Corn-Hilliard equation. Okay. So, let us write the script for doing the diffusion. So, diffusion FFT dot OCT. Okay. So, what is the thing? So, first I am going to clear all CLC, CLF. So, I am going to clear all variables, functions, everything. So, start with this thing. So, number of grid points is 32. When we are doing Fourier transforms, we always want this number of grid points to be 2 power n. Okay. So, that is very important, and I am going to take dx to be equal to 1. Okay. So, what I am going to do is that, so I am going to put the same profile for I equal to 1 to n end for. So, what I am going to do is that I am going to say C of I is nothing but 0.5 into 1 plus sine of this quantity. What is sine? 2 into pi into m into I into dx divided by n. Okay. So, this is the initial sinusoidal profile that I have made. So, I am going to plot this, and I am going to plot it with the red line, and I am going to mark it as initial. Okay. So, this will be plotted and it will be written as the initial profile. So, I am going to hold on, so that when I plot the next profile, the final profile, we will know how it is. So, I am going to define an half n, which is nothing but n by 2. Okay. So, del k, so we have to discretize in Fourier space, and in Fourier space discretization is the delta k is, so 2 pi will be split into this n, which is the 32 that we have taken. Okay. So, whatever be the number of points that you take, so much will be the discretization in the Fourier space. Okay. So, that is the del k that we have taken, and I have to define a time step. I can define a larger time step. I am defining 0.5 because this is an implicit technique. So, I am going to say for m is equal to 1 to 80. So, we are going to go the same 40 time steps, c hat, which is the Fourier transform of c. Okay. So, and for I is equal to 1 to n. So, in the Fourier space, what we are going to do, if I minus 1 is less than or equal to half n, k, which is the vector, is I minus 1 times del k, and if I minus 1 is greater than half n, then k is equal to I minus 1 minus n into del k. So, this is the place where we have implemented the periodic boundary condition. The reason why we have taken I minus 1 is we want to include the k equal to 0 point. Okay. That is, in the Fourier space, we are having minus pi by a to pi by a all k values. So, basically that minus pi by a to plus pi by a is taken by making sure that if it is half n, we are going to take k to be positive. If it is greater than half n, then we are going to subtract n, so that it becomes negative. So, this is the two parts, and while doing that we want to incorporate the 0 point also. So, that is done by taking I minus 1. Okay. So, that is the periodic boundary condition implementation. So, once we have k, we can calculate k squared as k into k. Okay. So, now we have k squared, because we are solving the diffusion equation, k squared is all we need. So, c hat of I is nothing but c hat of I divided by 1 plus 2 into k squared into delta t, right. So, this is okay. You do not see why we should have a 2, no, it is d k squared delta t. So, 2 is not needed, at least not in this part. So, end for. Okay. So, we started the time loop, we Fourier transformed f, and we calculated the vector, and we calculated k squared, and the evolution is c by 1 plus d k squared delta t. So, that is what we have taken. And for what do? We take the composition to real space, this is real of IFFT c hat. Now, it is really not necessary in this case at least that you can take this Fourier transform outside the loop, you can do everything and then you can come back to real space and come out. but the reason why I have done both the Fourier transform and the inverse Fourier transform inside is that this becomes essential if you are doing the Cahn-Hilliard equation. So, it becomes easier to then compare. The other reason is there are numerical errors that can creep in. So, you take the C to Fourier space and you keep doing this. So, the function is completely real in real space, but it might accumulate some imaginary parts. So, by doing this every time Fourier transforming back and taking only the real part, then we are making sure that those errors do not grow. So, that also becomes important sometimes. Okay. So, now I say plot C. So, this is the code which will do diffusion equation using Fourier transform, right. So, I say diffusion f of t dot OCT. Okay. So, there is some error. Okay. The error is here. So, plot C, it should be comma. Okay. So, there is an extra. So, the if loop, if I minus 1 is less than half n, yeah, here there is a this thing that is missing. So, let me put that. If I minus 1 is greater than half n, so that completes. Okay. Okay. So, first thing you notice is that the solution came out very fast, because instead of running 40,000 I am just running 80 type steps, and you can see it is the same solution. So, this is the initial profile I had and this is the final profile I have, right. Initial profile was red in this case and final profile which is blue. So, you can see that it is going towards homogenization. Now, let us go do the same thing, same initial profile, and okay, let me copy the diffusion dot FFT to Cahn-Hilliard FFT dot OCT. Okay. Now, Cahn-Hilliard FFT dot OCT, what is the difference? So, the difference is that now we have to calculate a G and we need to do Fourier transform on that. So, clear all CLC, CLF, n is 32, dx is 1, m is 1. So, they are all the same. So, we have taken that and we have taken the initial profile. I have plotted the initial profile and I said hold on, n half n, then del k I have defined, dt I have defined, and I go to inner loop. The first thing that I have to do is that h is equal to, I have to define what is, so we called it G, so let us call it G. G is equal to 2 into C into 1 minus C into 1 minus 2C. Okay. Now, so this is should be all dot star 1 dot minus C dot star 1 dot minus 2 dot star C. Okay. So, it is very important, so that each component wise it does and it saves it as G. So, now G hat is nothing but f of t of G, right. C hat is f of t of C. So, now we go in and we do the same thing. So, we define the k vector and we calculate k squared, but we also need k power 4, which is k squared into k squared. Now, C hat is nothing but a C hat. Okay. So, now we have this minus k squared dt into k squared into g hat, right. So, we have that divided by 1 plus 2 into k power 4. So, this is the 2 is coming from the fact that when you write the Cahn-Hilliard equation, you have this kappa del c squared. So, you get 2 kappa del squared c. So, this 2 is coming from there. So, kappa is 1, but we have taken 2. So, sometimes people take kappa to be half, so that also becomes 1, but we have taken it to be kappa to be 1. So, this 2 is coming from the Cahn-Hilliard equation, which is 2 kappa del power 4 c. Okay. So, that is the 2 that we have it here. Okay. So, 1 plus 2 kappa del t. So, we have, and again we, so this is the reason why in the previous case also I put this Fourier transform of C and the inverse Fourier transform of C inside the loop, because unless the C is in real space you cannot calculate G in real space, and after that only it has to go to the Fourier space. So, that is the reason why we did. So, we go and we save this. Okay. So, now let us run this. So, Cahn-Hilliard FFT.OCT. Okay. So, there is a problem. What is the problem? Line 26 column 9. Okay. C hat is equal to C hat I. Okay. So, G hat I have to say I, right. So, for every I it has to do, it does not know which I it has to do. So, okay. Okay. So, now you can see that I started with an initial profile and my profile has become like a box profile. Okay. So, this is the solution of the Cahn-Hilliard equation. Please remember, when we solved the diffusion equation, the initial profile was like this and the final profile was something that was going towards homogenization. Now, we have the A rich regions becoming richer in A and B rich regions becoming richer in B, rather the other way. So, this is the B rich region, this is the A rich region. So, they are becoming richer in B and richer in A respectively, and you have this interface that is formed between the A rich region and the B rich region. So, interface region is the region where the composition changes continuously, whereas in the bulk, I mean the A rich region and the B rich region, it goes to the compositions of 0 and 1, which is the bulk composition respectively. Okay. So, it is still not evolved completely. So, when it evolves completely, you will see a perfect one which is going to 1 and then it will have an interface and it will go to 0 and it will come. This is what we have looked at, but this will not happen for all wavelengths. To show you that, I would like to change the number of wavelengths. So, let us try to do that. Cahn-Hilliard FFT dot. So, let us make m equal to 2 and let us see what happens. Okay. Sorry. Okay. Okay. So, initial profile has two this thing, and you can see that the final profile is actually going towards like in the case of diffusion, right. So, this is coming down instead of becoming a box profile. Okay. And you can see, suppose if I make it m equal to some 4, that is still smaller wavelength, then you will see that it becomes okay. So, this is the initial profile, everything has become flat. So, which means in the case of Cahn-Hilliard, depending on the wavelength, some wavelengths are going to grow. You saw one wavelength m equal to 1, that wavelength grew. M equal to 1, the wavelength was 32, because we are taking a system size of 32. Now, when I make 4 waves, the wavelength is 8 is not growing, and we also saw one with 16 when I took m equal to 2, that was not growing. Okay. So, this clearly indicates that in this case certain wavelengths will grow, certain wavelengths will not grow, and the smaller wavelengths will be the ones which will not grow. The lowest wavelength that grows basically sets the wavelength limit, above that everything will grow. 32 grows. So, if you have something like 40, 64 and 128, they will all grow, but whatever is less than 32, 16 itself was not growing. So, the rest of them will not grow. So, this is the solution for the Cahn-Hilliard equation. Unlike diffusion equation, diffusion equation, the 32 itself was going, and anything higher you take also will grow. So, whatever be the wavelength, they will all go to homogenization. That is the nature of solution in the case of diffusion equation. In the case of Cahn-Hilliard equation, it can go to this homogenized solution, or it will grow depending on what is the wavelength that you are considering. Okay. So, this is important, this is what we discussed by looking at the growth rate r beta, and this is getting the same thing numerically. Okay. Now, there is one last piece I would like to do with this before we end this lecture. So, in the next part of this lecture, I would like to take the Fourier transform code for Cahn-Hilliard and try to calculate what is the interfacial energy for the system. Okay. So, this system supports interfaces. When m equal to 1, for example, it supported an interface, and I would like to set up a system in which I will produce two interfaces, and I would like to find out what happens to the interfacial energy. So, that is what we will do in the next part of this lecture. Thank you.